Section 7, Part B. Okay, let's look at an example of how all these ideas come together. So for the sake of argument, let's say that our population is everybody in the United States vis-a-vis, do you like action movies? And then our parameter will be the proportion of everybody in the United States who would say yes. So I'm not going to parse words too much at the moment. We'll talk about it a bit later. Our parameter is the proportion of everybody in the United States that likes action movies. More specifically, it's the proportion of everybody in the United States who would say yes when asked, do you like action movies? And so there you go. Sample, parameter, proportion, everybody in the United States, parameter, proportion of people in the United States who would say yes, they like action movies. Now, for the sake of argument, let's say that 60% of everybody in the United States likes action movies. That is to say, the proportion of people out there who like action movies is 0.6. That is to say, the probability of a yes is 0.6. Now, bear in mind, if we knew this, we wouldn't be sampling. But you've got to be able to walk forward before you can swim backwards, right? So, for the sake of argument, 60% of the people in the United States likes action movies, but we don't necessarily know that. This is our parameter. P is 0.6. Now, lowercase p is a good letter for parameter. I don't want to talk too much about the notations that I'm going to be using in this example. We will talk about them in more detail in the next section. But for what it's worth, lowercase p is a good letter to use for parameter. P for parameter, P for proportion, P for probability. Because it is probability, right? The first time you pick a person, there's a 0.6 chance of them saying yes. And having taken one person away from hundreds of millions and put them to one side, the second time you go to pick somebody, effectively there's a 0.6 chance of a yes, and so forth and so on, right? And for any number of people that we could actually ask, that's still the case. We're not going to be taking away any noticeable chunk of the United States. So effectively, this is the probability of getting a yes every time we pick. Up to a few thousand picks, right? As long as we're not taking away a noticeable chunk of the United States. Now what we'll do is we'll take a simple random sample of 2,000 people picked from the United States. Now remember what this means. Every possible group of 2,000 Americans you could create has the same chance, not change, has the same chance of being the group actually selected. Now again, what am I not saying? I'm not saying divide the population of the United States up into groups of 2,000 and pick one. I'm saying every possible group, right? So you're in some of those groups, you're not in some of those groups. There's an unthinkable large, there's probably no name for that number. There's an unthinkably large number of groups of 2,000 you could make from hundreds of millions of Americans, right? But for the sake of argument, every possible group of 2,000 Americans we could create has an equal chance of being selected. Now again, that is an ideal. You're never going to know for sure the simple part of the simple random sample. You're never going to know that every possible group of 2,000 Americans that you could pick has the same chance of being picked. It's an ideal. There are certain things you do to minimize the chance of it's going wrong, but at some point you've got to take it on faith. So we have, if you could wrap your mind around every possible group of 2,000 Americans and study them, then you've just done something orders of magnitude harder than asking everybody in the United States, which was impossible in the first place. It's an ideal. So the statistic will be the number that comes from the sample. In this case, we have two statistics, or rather say we have one statistic and two different ways of looking at it, unit changes. On the one hand, we can talk about the number of yeses. And to tie this together with the notations that we'll develop in Section 8, again, for the moment, the notations are not the important thing, the concepts are. We'll call it capital X. It's a good thing to call it. Well, among other things, it is a random variable, right? You're going to do something random and get a number. You're going to randomly pick 2,000 people and get the number of yeses. So depending on what 2,000 people you actually pick, you're going to get a different number of yeses, right? So it is a random variable. We have done something random and we have gotten a number. Ergo, X is a good letter for it. So let capital X be the number of yeses that you actually get. Now bear in mind, it could be 0 or 1 or 2 or 3 or or 199 or 2,000, right? So number 1, it's a random variable. Number 2, yes, it is technically a discrete random variable, right? There is a probability of it being 0, there is a probability of it being 1, there is a probability of it being 2, and there's a probability of it being 2,000. But most of those numbers are 0.000 something, right? They're very small. Remember, they've got the 2001 columns, each with a probability under it, are all at least 0, and they've got to add up to 1. So the biggest of them is very small. They're all 0.00 something. So it is technically a discrete random variable, but back on planet Earth, we're not going to look at it that way, right? We are never at any point going to have a chart with 2001 columns and probabilities below them that read 0.0000 something, right? It's just too complicated. So technically, we talked in section 5, early section 5, about the technical difference between a discrete and a continuous random variable. And then I talked also about the practical difference, right? X is technically a discrete random variable in the sense that there's 2001 different numbers it can be. And yes, if you wanted, you could list the probability of each one directly below. Thing is, I don't want, right? I mean, when we were doing our people who weren't left-handed, or coins that may or may not have been heads, and we looked at the number of left-handed people when we pick 4, or the number of heads when we pick 3, sample sizes of 3 and 4 were hard enough to work out the charts for, right? And 5 and 6 and 7 required combinatorics, factorials, and combinations, and things we're not going to talk about in this course. So you can just imagine what a sample of 2,000 would be like to figure out that chart. The samples of size 3 and 4 and 5 were bad enough. In fact, in some of those 5 was even a non-starter. So we're not going to be working out charts like this anytime soon. Nobody in their right mind is going to be working out charts like this anytime soon. Yeah, you could do it with computers, but even there, let us assume for the sake of argument that you have each one of those probabilities at your fingertips. Well, you've still got 2001 numbers to write down underneath them, right? 2001 probabilities to write underneath them. And by the way, they're all negligible, right? They're all 0.000 something. 2001 slivers, each of which together add up to 1. You know, the tallest sliver is still very thin. So any individual number, even the most likely number, whatever that is, (1200). Any individual number, even the most likely number, call it 1200, is going to be extremely unlikely. So we are close enough to a continuous random variable, right? If X can be hundreds and hundreds of different things between 0 and 2000, then it is close enough to say that X can be anything between 0 and 2000. Is that true? Can X literally be any real number between 0 and 2000? No. You can't get pi number of people saying yes. You can't get 451 and a half people saying yes. That doesn't make sense. 451 and a half. But bear in mind, nobody really cares whether it's 450 yeses or 451 yeses. They're practically the same thing in context, right? And they're both very, very unlikely individually. So when you've got that many different things between 0 and 2000, individual possibilities are negligible. That is to say, if you made a probability histogram of it, it's not very jaggedy, right? And we've seen this before, right? The number of blue-eyed people when you pick 4 is comparatively jaggedy. But the number of blue-eyed people when you pick 80, and this is not complete, it theoretically goes anywhere from 0 to 80, but these bars are so insignificant that you're not even seeing them, is comparatively smooth. So at some point, when you can be many, many different things between smallest and biggest, the shape becomes more important than the individual bars. You see, here it's the individual bars that count, because whether or not it's 1 makes a very big difference, even 2. Whether or not it's 2 makes a very big difference, right? This or this or this is a very different answer from this or this. Less than 2, this or this. At most 2, this or this or this. You know, they're 0.15 away from one another. They're very different answers. But, you know, less than 21, at most 21, well, how much are you going to change your answer if you add in this particular bar? And again, this is not really perfect. There's a lot more bars than this, and it's a lot smoother than it looks here. But it's enough to give you the point, right? At some point, the shape becomes more important than the individual bars. At some point, you stop thinking about individual possibilities. So there is the practical distinction between a discrete random variable, between a very discrete random variable, and something that is close enough to being smooth, something that is close enough to a continuous random variable. Individual bars are what we're talking about. This or this or this or this or this. Here the shape becomes more important than the bars. And the shape that you're looking at should give you an idea where we're going with this, but we'll tie it together in the next section. So for very large samples, and here we're talking about 2001 bars, right? So whatever the shape looks like, 2001 bars, each of which is, you know, insignificant in width, and each of which is practically the same height as the next one or the previous one. You've got a very smooth picture, right? So it's close enough to smooth. It is close enough to true to say that you can be any real number between 0 and 2000. If you can be many, many different things between A and B, then for all practical intents and purposes, you can be anything between A and B. Very little harm is done by treating that picture you just saw as a smooth curve. A lot of harm is done by treating this one as a smooth curve. Now, what is the beauty of this, of course, is that in the real world, for all sorts of reasons, for the moment, let's say common sense, but we'll justify it as we go on, you're not going to ask 4 people who they're going to vote for. You're not going to poll 4 people to get the proportion of left-handed people in New York. You're not going to flip a coin 4 times to get an idea of whether it's a fair coin or not, right? There's all sorts of practical reasons, which we'll talk about, why we want to do large samples, and least of all is that they're very smooth. Individual possibilities are not so jarring when you do large samples. So yeah, if you're talking about picking 4 people, whether they like action movies, then you're talking about bar or bar or bar or bar or bar. But if you're talking about 2000, at some point the relatively smooth picture becomes more important than the individual bars. So for all practical intents and purposes, X is a continuous random variable. For all practical intents and purposes, you can get any number of yeses between 0 and 2000. Now, the proportion of yeses is a more useful perspective on all this. Technically, it's a different statistic, but really it's just a unit change on the previous statistic. It's the same concept, it's just a different way of measuring it, and we've beaten that to death, right? The proportion of yeses, that is to say the number of yeses divided by 2,000, can be 0 over 2,000 or 1 over 2,000 or 2 over 2,000 or 2,000 over 2,000. So effectively it's the same bars, just shrunk 2,000 times in height. Or alternately, just scale things a little differently. It's the same basic picture, right? We're just labeling it differently. Depending on your perspective, the number of blue-eyed people you get when you pick 80, the proportion of blue-eyed people that you get when you pick 80, well, on the one hand, you could say it's the same picture, but shrunk down 80 times its present height. On the other hand, you could say just keep the picture and relabel this scale, 0 over 80, 10 over 80, 20 over 80, 30 over 80. It's a unit change. If you superimpose them, yes, it's 80 times smaller, but it's easier to think, as we said in the past, of just relabeling the scale. So all it is, it's the same concept. It's just a different perspective on it. Number of yeses, proportion of yeses. Now, a good thing to call, and again, we'll talk more about the notations in Section 8, but a good thing to call the proportion of yeses in the sample is p hat. This is a little hat symbol. It's a little hat symbol on the p. We call it p hat. The idea of hat in statistics basically means estimator of. Remember what the goal of this guy is. The proportion of yeses in the sample is supposed to estimate the proportion of yeses in the population, which was 0.6. So with that in mind, the hat is a good thing to call it. P hat for this, for the statistic, for the estimator. P for the parameter, the estimated, the thing we're estimating. But again, we'll talk more about the notations in the next section. Suffice to say, we've got two statistics, or if you like, two perspectives, two unit changes on the same statistic. To go from counts to proportion, divide by 2,000. To go from proportion to count, multiply by 2,000. It's just a unit change. Now, for the sake of argument, let's say, now bear in mind, we're presuming that 60% of people out there like action movies. And that everybody tells the truth, but we'll worry about that later. For the sake of argument, let's say that 1120 people say yes. Well, then x in this case is 1120, and p hat in this case is 1120 over 2000, which is evidently 0.56, but I've learned not to trust my notes. So 1120 divided by 2000 is sure enough 0.56. Now bear in mind, we do not know this. It is the truth, but we do not know it. That is why we're trying to sample. That is why we're estimating it. If you knew this, you wouldn't have to estimate it. It is the unknown truth. It is true, but we don't know it. So this is our sample result, and this is our estimate. We estimate that 56% of the people in the United States like action movies. 56% of the people we asked like action movies, so probably about 56% of everybody likes action movies. Let me say that again because, number one, it is a very good way of thinking about things in common parlance. 56% of the people we looked at liked action movies, therefore probably about 56% of everybody out there likes action movies. But number two, that's not really true, right? Remember what I said in the previous video. This is a parameter. There is nothing probably about the proportion of people in the United States that likes action movies. It is not probably 56%. It is not probably anything. It is what it is. There is nothing random about the percent or proportion of people in the United States who like action movies. It is what it is. It's a good way of saying it for just verbal purposes. Probably about 56% of everybody likes action movies. It would be a little bit more accurate to say that we estimate that 56% of people like action movies. And the technical term here is confidence. We'll talk about in later sections. We are confident that about 56% of people like action movies. Technically, we're not probably that it's anything. But just as a way of absorbing the general information, it doesn't do a great deal of harm to say it that way. Now, the downside of the simple, and of course the reality is that it's 60%, so we're not quite right. And that was always going to happen, right? You were probably not going to hit it dead on. On the one hand, and we haven't justified any of this yet, but I think it's common sense. Since 60% of people like action movies, if we ask a lot of people, on the one hand, we're probably going to get something close to 60%, right? Is this? Well, what do you mean by probably? What do you mean by close? We'll worry about that later. So on the one hand, if 60% of people in the United States like action movies, we're probably going to get something close to 60%. If we poll a lot. On the other hand, if we poll a lot, there are too many different things that can happen, right? It's not this picture, but it's a similar idea. 2001 bars, right? The idea of hitting exactly anything dead on is pretty slim. If you poll 1 million people, you could probably get away with that in the United States. I mean, you know, hundreds of millions of people. Doesn't really take a bite. So if you poll 1 million people, you're probably not going to get, that was easier than, I didn't really need a calculator for that. If you poll 1 million people, you're probably not going to get 600,000 saying yes, right? If you poll 1 million people, you're probably not going to get 600,000 yeses. It's too on the nose. You're probably not going to get anything very far from 60%. But there's a lot of things that count as close to 60% when you're talking about 1 million. And it's probably not going to be that on the nose, right? On the nose would be 2,000 times 0.6, which is 12%, which is not what I just got. Actual 2,000 times 0.6, which is still 1,200. On the nose would be 1,200, and it was probably not going to be exactly 1,200. Are we close to 1,200 yeses? Is this close to 60% yeses? Well, what do you mean by close? It is what it is. It's what we got. So the downside of the simple random sample, for one thing, you're never going to get it on the nose. I mean, theoretically you could, yes, but it's highly unlikely. It wasn't going to be exact. We estimate 56% of people in the United States like action movies. The truth is 60%. So depending on your perspective, we're close or we're not that close. We won't haggle over what close means, but it is what it is, right? The downside of the simple random sample is that sometimes you'll get an unusual sample. The upside, that is to say, far from the truth, far from the parameter. The upside of the simple random sample is that, what does unusual mean? Unusual means it's probably not going to happen, right? That is the definition of unusual. So on the one hand, yes, you could get a very unlikely sample. On the other hand, you're probably not going to get a very unlikely sample. That is what very unlikely means. Fair enough? So yeah, you could get anything, right? Now, bear in mind, we are talking about hundreds of millions of people. 60% of hundreds of millions, 40% of hundreds of millions. Suffice to say, there are millions and millions of yeses out there, and there are millions and millions of no's out there. A simple random sample of 2,000 means every possible group of 2,000 Americans has the same chance of being selected, right? So some of those groups are going to be most of those groups are going to be comparatively typical, whatever that means, and some of them are going to be very unusual. But you're probably not going to get one of the unusual ones. That's what unusual means. On the other hand, What if you do? Bear in mind, we don't know the 60%, so we have no way of knowing whether this is unusual or not. It probably is not unusual, but what if it is? We have no perspective on this if we don't know the 60. Maybe it's a typical sample, in which case we're close to the truth. There's a small chance it's an unusual sample, in which case it's very far from the truth. Point is, you could get any sample, right? You could get any group of 2,000 Americans, and there's millions of yeses, there's tens, hundreds of millions of yeses out there, and there's tens, hundreds of millions of no's out there. So with room to spare, to put it mildly, you could get 200 yeses, or you could get 200 no's, or anything in between. We established that 2,000 yeses or 2,000 no's. We established that in the first place, right? So yeah, you could get an unusual sample. You could get 2,000 yeses, you could get 2,000 no's, and bearing in mind we have absolutely no idea what proportion of people in the United States like action movies, we have no perspective on whether this is a typical sample or an unusual sample. What do we know for sure? We know two things for sure at this point, both of which are a little sarcastic. On the one hand, we know that somewhere in the United States there are 1,120 people who like action movies. On the other hand, we know that somewhere in the United States there are 880 people who don't like action movies. I don't want to get too sarcastic about this, but that's a lie. I do. Because I want to make a point. We can't know anything for certain. If it's certainty you're after, Dr. Tyree's philosophy class is down the hall, to quote Indiana Jones. Now, bear in mind, let's play the sarcasm game, because that's how you learn. If it's certainty you're after, we know that somewhere in the United States there are 1,120 people who like action movies. It is cosmically unlikely that we have just picked the only, if it is a simple random sample, then it is cosmically unlikely that we have just picked the only 1,120 people in the United States who like action movies. But what if we did? Well, if there are only 1,120 out of millions and millions of people who like action movies, then P is effectively 0. For all practical intents and purposes, 1,120 out of hundreds of millions would say yes. Practically everybody out of hundreds of millions would say no. So the proportion of people who like action movies is effectively 0. Well, pretty close. Let's play the game the other way. What if we have just picked the only 880, that is 2,000 minus 1,120. What if we've just picked the only 880 people in the entire United States who don't like action movies? Well, then effectively, pretty much everybody in the United States likes action movies, and P is basically 1. So, not to be too sarcastic about it, but what do we know for certain at this point? From this sample, we can conclude with certainty that the proportion of people in the United States who like action movies is somewhere between none of them and all of them. And to be brutally honest, I didn't need that sample to know that. So if it's certainty you're after, we now know a grand total of nothing. We are playing the odds. You're almost certainly not going to pick the only 1,120 people in the United States who like action movies. You could. You're almost certainly not going to pick the only 880 people in the United States who don't like action movies. You could. So for sure, for certain, we don't know anything. But if we're playing the odds, probably about 60% of the people in the United States like action movies. Or to be more accurate about it, probably about 56% of the people in the United States like action movies. Or to be more accurate about it, that is our estimate of what it is. Or to be more accurate about it, we're confident that it's about 56%. More on that in section 11. So we're playing the odds. If it's certainty you're after, you're not going to get anything. Now let's see, what do I say here? Note that saying that every possible sample is equally likely. Oh, yes, this is the other point I wanted to make. This sometimes confuses students. It is one thing to say that every possible group of 2,000 Americans is equally likely, which is true if it's a simple random sample. It is quite another thing to say that every one of these numbers is equally likely. Nothing could be further from the truth. Whatever you get, it's almost certainly not going to be all 2,000 of them, for instance. This is highly unlikely. Even compared to other individual possibilities, it's highly unlikely. It's a lot more unlikely than, say, 1,207. So it's one thing to say that every possible group is equally likely. It's quite another thing to say that these numbers, the possibilities for x bar or the possibilities for p hat, are all equally likely. Remember, there are a lot of groups out there where all of them would say yes, but they are still far and away the exceptional groups, right? There are a lot more groups out there where 1,200 would say yes than there are groups where 2,000 would say yes. Ergo, 1,200 is more likely than 2,000. So we're not remotely claiming that everything x can be is equally likely. We're not remotely claiming everything p hat can be is equally likely. All we're claiming is that every possible group is equally likely. There's a lot of groups of zeros. There's a lot of groups of all no's out there. All 2,000 say no. But there's still the unusual groups. There's far fewer of them than, say, groups where 1,190 would say yes, and so forth and so on. So that's one thing you want to bear in mind. How do I put it here? Note that saying that every possible sample is equally likely is not the same as saying every possible numerical result is equally likely. There are a lot of groups where they would all say yes, p hat is 1, but they're still very exceptional and you're highly unlikely to get one. There are a lot more groups where 1,200 would say yes. Now again, exactly anything is unlikely, but getting 1,200 yeses, getting 2,000 yeses is a lot less likely than getting 1,200 yeses. Exactly anything is pretty unlikely, but shall we say 1,200 is the least unlikely possibility for x? The point is that the statistic is random. It depends on what sample you actually pick, and like all randomness, it obeys certain probability rules. A statistic, whether it is the number of yeses, where the numbers are not so microscopic, or the proportion of yeses, which for the long run is a more useful perspective, but the numbers are very small, 0.00 some. Every statistic, whether it's the number of yeses or the proportion of yeses, every statistic is the result of a simple random sample, and you get a number from it, right? You do something random, you get a number. A statistic is a random variable, and therefore all the stuff we said about random variables in section 5 and 6, in particular 5, is still true. Like any random variable, it has a pattern of its randomness, a shape, and it has a center to its randomness, a mean, and it has a spread to its randomness, the standard deviation of the random variable. Every random variable, whether it's x bar or p hat in this case, every random variable has a shape to its randomness, and this guy has a mu, and this guy has a sigma. Shape, center, spread. As usual with probability, we have three perspectives. Point is that whenever you do something random, all randomness has a shape, has a probability distribution, has certain rules that it obeys, what it's likely or unlikely to be. Now we've got an inkling of what's going on here, right? Presumably this is going to go up and peak out at 1,200, or 1,200 over 2,000 if you prefer. and then go down again, right? So that you're probably going to get something in the neighborhood of 1,200 yeses, and you're highly unlikely to get something very far away from 1,200 yeses. Well, for the moment, it's just a presumption, but let's say that that's the case. Then that's the shape of its randomness. Other randomness can have very different shapes, as we've seen. So with probability, you always have the same three perspectives. The probability of it being the thing the next time, the proportion of many repeats where it would happen, the proportion of all possible repeats where it would happen. It's the same three perspectives always with probability. Let's take them one at a time. So let's take our p-hat statistic. Effectively, it could be anything between 0 and 1. At a wild guess, it'll probably be close to 0.6, but there's no guarantees. A single p-hat will vary with certain probability rules. The proportion of yeses you're going to get when you ask 2,000 people in the near future might be anything between 0 and 1, will probably be close to 0.6, that's a presumption. But it's got a shape to its randomness. It's got certain probability rules you obey, and it will depend on what sample you actually pick, right? If you pick a different 2,000 people, you're going to get a different number for p-hat. So let's go there. Perspective 2. The first time we pick 2,000 people, 56% of them say yes. Long story short. The next time you pick 2,000 people, 62% of them say yes. The next time you pick 2,000 people, the next sample you pick of 2,000, 59% say yes. The next sample, 61% say yes. 63%, 14%, 57%, 59%, 60%, 92%, 61%, 58%. Notice again that for verbal purposes, percent is a little easier than proportion. Just be clear on which one you're using. Now, bear in mind that with replacement, without replacement, it doesn't make a great deal of difference, right? With hundreds of millions of people to pick from, you could pick 2,000 over and over and over and not make a dent in what's out there. But if it's really going to bother you, put them back after you pick the 2,000, scramble them up, and then pick the next 2,000. And we can do that pretty much indefinitely. So, now, and bear in mind also that when you're picking an actual group of 2,000, the with replacement, without replacement is totally meaningless, right? If you're picking 2,000 people from the United States, then the odds that you pick the same person twice are not worth bothering with. But let's say that either way, you pick 2,000 people and put them to one side. So they're all different people. Now, as we do lots of samples, and I'm not telling you exactly what lots is, but enough of them to make it interesting, a pattern begins to emerge, right? Bear in mind, we don't know this, right? So we have absolutely no perspective on how typical the 56 is. We have no perspective on how typical the 62 is. We have no perspective on how typical the 59 is. But now we're beginning to get an idea, right? And then you hit the 14. So if you start with the 14, if that's the first sample, then you're pretty much screwed, right? Because we're only going to do one sample. But on the other hand, if we're not really going to do more than one sample, but for the sake of argument, if we did lots of samples, then you would eventually see a pattern emerging. Now, I can't tell you what eventually is. We've talked about that point before. Suffice to say, without spinning our wheels entirely here, the longer you let it go on, the less likely it is that a pattern doesn't emerge. Eventually, a pattern emerges as we do more and more samples. Or, if you want to be mindlessly pedantic about it, it is highly unlikely that a pattern will not eventually emerge. And it is infinitely unlikely that the pattern will not emerge eventually. So, sooner or later, as you do lots of samples, a pattern begins to emerge. And now we've got some perspective on this, right? Note the yellow. Once we have a lot of samples, about 60, about 60, about 60, about 60, whoa, about 60, about 60, about 60, whoa, about 60, about 60, about 60. Now we've got some perspective, right? This is an unusual sample, or this is an unusual, and this is an unusual sample, and this is an unusual sample. The yellow ones are the unusual ones. Now, again, if you want to be sarcastic about this, there is no reason that one of these yellows couldn't be the typical sample and the others are all the unusual ones. But again, as always, we're playing the odds, right? The longer you let it go on, the more you begin to see what's going on. It's bouncing around 0.6, and once in a while, not very often, but once in a while, you bounce far away. What do we do with data? Well, we can make a histogram. So once we've got a lot of samples, enough to make a histogram worthwhile, then we can make a picture. And I'm not telling you what shape you're going to get, and I'm not telling you how many bars you ought to use here. All I'm saying is that you can make a histogram of your results. And for the sake of argument, let's say that it's peaking around 0.6. For the sake of argument, let's say that it's unimodal, roughly symmetric. It may or may not be, but for the sake of argument, let's say that it's unimodal, roughly symmetric, and it peaks around 0.6. So that your typical sample is bouncing relatively close to 0.6. And then once in a while, you get a sample that bounces very far away from 0.6, but it's not very likely, right? A pattern emerges. As we do lots of samples, a pattern emerges. You can see the pattern here in general terms, but when you've got the picture, you've got a very good idea. You can see which results are typical and which results are unusual. Now, ideally, what we'd like to see is the histogram centered at 0.6, with the 14 and the 92 in unusual territory. But remember what randomness is. There are never any guarantees. That's what random means. So there's a lot of things that can go wrong here, and the least of which that can go wrong is that when you pick a person, it is random. When you randomly pick 2,000 people, the result is something random. When you randomly pick so many samples of 2,000 people, the result is still something random, right? The more levels up we take this, the more everything smooths itself out, probably. But strictly speaking, you could get one unusual sample. Strictly speaking, you could get 30 unusual samples in a row. There are no guarantees. But the further up we take this, the more levels we take it, the further out we go, the more likely it is that a pattern eventually emerges. And let's say that it is the pattern that, let's say that there is something true about the pattern, more on that in a minute. What we'd like to see is that it's bouncing around 0.6. It would be nice if it was symmetric, you may not have that, but we would at least like to see that it balances. Remember, balance doesn't require symmetry necessarily. We would at least like to see that its balance is at 0.6, that the mean of this data is 0.6. Any way you want to say that. We'd at least like to see that it's bouncing around 0.6, that it's centered at 0.6. But you may not get that. We'll talk more about that in a minute. So perspective 3, to recap, perspective 1, the probability that the random thing will be this, that, or the other. Perspective 2, do the random thing many, many times and a pattern eventually emerges, or it's highly unlikely that it won't. Perspective 3, all conceivable p-hats from all conceivable samples of size 2000. Now, bear in mind it doesn't matter in the slightest whether this is a finite number of possible samples or theoretically infinite. How many possible groups of 2,000 coin flips can you do? Well, as many as you like. How many possible groups of 2,000 people from the United States can you pick? Well, practically as many as you like, right? There are no words for the number of samples of size 2,000 you could pick from hundreds of millions of people. It's effectively infinite. It doesn't really matter whether it is effectively infinite or theoretically infinite. It's still unthinkably big. there are many, 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 no words for it, many possible samples of size 2000, even from a technically finite population like the United States. So this is not something you're going to be able to wrap your mind around, as always. As always, the first perspective is what probability is the probability we're talking about. The second perspective is approximately what probability means. And the third perspective is the technical definition of probability. So in your mind's eye, only in your mind's eye, you could never really do it. But in your mind's eye, let's conceive every possible example of the statistic from every possible sample of 2,000 Americans, and we'll make that picture. And a pattern emerges. Well, there is a pattern. It may or may not be the pattern you're looking for or expecting, but out there at infinity, out there at every possible instance, as always, there is some kind of pattern. It is what it is. It has the shape it has. And this is what we call the sampling distribution of the statistic. The sampling distribution of the statistic is the pattern formed by every possible instance of the statistic from every possible sample. Doesn't matter whether it's a finite number of possible samples or an infinite number of possible samples. It's an ideal, as always. If you could actually do every possible sample of size 2,000 Americans and tally up the results, congratulations, you've just done something a billion times more harder than asking everybody in the United States, which was impossible in the first place. It's an ideal. Orders of magnitude worse than the original dilemma of asking everybody in the United States. Nevertheless, out there at infinity, every possible example of the statistic, there is a pattern that is formed. It may or may not have this shape, it probably will. And it may or may not be centered here, but there'll be some kind of a shape. And that shape is the sampling distribution. Now, bear in mind, we are not interested in every possible sample. We are not interested in 30 samples. We are interested in the one and only sample that we are going to do. As always with probability, bullet point 2 and bullet point 3 are simply ways of wrapping your mind around bullet point 1, right? Because that's what probability is. If 30% of whatever number on the scale this is, 0.4, whatever, if 30% of samples give you something less than this, then that is exactly the same as saying there's a 0.3 probability that the sample you're about to do will give you something less than this. If 90% of samples give you something between here and here, that's the same as saying there's a 90% chance that the sample you're going to do will give you something between here and here. Bear in mind that in the end it's the same thing, right? If half of samples give you something less than 0.6, which certainly looks to be the case here, then that's the same as saying that there is a 1/2 chance the sample you're going to do is going to give you something less than 0.6. In the end, the sampling distribution is just a way of wrapping your mind around the probability distribution of p hat. That is what probability always is. The pattern formed by every possible p hat, the pattern of randomness for the p hat we're actually going to do. The one is exactly what we mean by the other. It is all in the end a way of wrapping our mind around the pattern of randomness of the statistic. Ideally, what we'd like to see is some symmetric bell-shaped thing centered at the truth. But we may or may not be seeing any of those things. The pattern formed by all possible samples, sampling distribution, perspective 3, is simply another way to look at the probability of a particular sample, probability distribution, perspective 1. That's what I just said, which is the idea we're really interested in, ending a sentence in a preposition. For instance, if half of all samples would give a proportion of yeses less than 0.6, what I just said, this is the same as saying that the sample we're about to do has a 1/2 chance of giving a proportion of yeses less than 0.6. As usual, this is simply what probability means, right? If you're unlikely, if a small proportion of samples give you something in this territory, then there's a very small chance the sample you're going to do is going to give you something in this territory. It's the same thing. We would like to see the histogram centered at that original truth, which is 0.6, even though we don't know that. However, this may or may not be true. This is getting on the long side, so I think I want to break it up here, and we'll talk about how this can go wrong in the next video. So we've got the basic idea of the sampling distribution of a statistic down. Bear in mind the p-hat is just an example that we're running for demo purposes. We'll worry about the notations and the math in the next section. The idea is the principles involved here. Shapes of randomness, shapes of many samples. Those are the important things to be taking in for the moment, not the numbers and the computations and the notations. We'll worry about those in the next section. So this is the basic idea of how all the stuff we've done in the previous sections comes together. And you begin also, I think, to see how section 3 is going to come back into this, but more on that in the next couple of sections. What I want to talk about in the last part of the section 7 video is the shape and spread of this guy's randomness. The center and the spread of this guy's randomness, the center and spread of the statistic. In other words, its mean and its standard deviation of that random variable, which is the statistic. And that and its implications we'll talk about in the next video